Reflexive Relations. Hello everyone. Today we are beginning our lesson on reflexive relations. To start, let's look at the big picture. In the study of relations, we are essentially examining how different elements within a given set interact or connect with one another. As we explore these interactions, you will find that relations can have various characteristics. One of the most fundamental and important properties a relation can possess is what we call reflexivity. Now, before we dive into the formal mathematical definitions in the next few slides, let's understand the basic concept. A relation is said to be reflexive if every single element in the set is related to itself. In other words, no element is left out. Each one must have a connection back to itself for the relation to earn this title. Formal definition. Now that we have a general understanding of what reflexivity is, let us move on to the formal mathematical definition. First, let us assume we have a set, which we will call set A, and this set must be non-empty, meaning it contains at least one element. A relation, which we will denote as R, defined on this set A is considered reflexive if every single element, let's call it, that belongs to set A is related to itself. To express this mathematically, we say that the ordered pair, a comma A, must be an element of the relation R for every element in set A. It is crucial to understand that this is a strict requirement. If there is even one single element, in set A such that the ordered pair, a comma A, is not an element of the relation R, then the relation R is not reflexive. With this formal definition established, we can now proceed to the next slide, where I will show you the specific logical steps to determine whether a given relation is reflexive. How to determine if a relation is reflexive. Now that we have established the formal definition, let us move on to the practical application. To determine whether a relation R on a set A is reflexive, you should follow these logical steps. Step 1. Identify the set A before analyzing the relation itself. You must first clearly list all the individual elements present in set A. This ensures you know exactly which elements need to be checked. Step 2. Identify the relation R next. Examine the set of ordered pairs that make up the relation R. This is the collection of pairings we will be testing against our set. Step 3. Verify the condition for every element. For every single element X in set A, you must check if the ordered pair X, X exists within the relation R. If you find that every single element X has a corresponding pair X, X in the relation, then the relation is confirmed to be reflexive. On the other hand, if you find even one single element X where the pair X, X is missing from the relation, then the relation is not reflexive. In the following slides, we will apply this step-by-step process to both a real-world scenario and a mathematical example to see exactly how this works in practice. Real-world example. Now that we have covered the formal definition and the logical steps to identify a reflexive relation, let us apply these concepts to a real-world scenario to make the idea more intuitive. Consider a set which we will call set A, consisting of a group of students in a classroom. On this set, we are defining a relation, R, as is the same height as. To determine if this is a reflexive relation, let us perform a step-by-step analysis. First, we identify the set. Set A is simply the collection of all individuals in the room, such as student 1, student 2, student 3, and so on. Next, we define the relation. In this context, two students are considered related if they have the exact same height. Now we must test for reflexivity. As we learned in the previous slide, for a relation to be reflexive, every single element must be related to itself. So, let us pick any student from the set, for example, student 1. We then ask, is student 1 the same height as student 1? The answer is obviously yes, as every person is naturally the same height as themselves. Since this logic applies to every single student in the classroom without exception, every element in set A is related to itself. Therefore, we can conclude that the relation, is the same height as is a reflexive relation. With this real-world example as a foundation, we will now move forward to look at some specific mathematical examples using sets of numbers. Mathematical example. Now that we have looked at a real-world scenario, let us apply the same logic to a concrete mathematical example to solidify your understanding. First, let us define our set, A, which consists of the elements 1, 2, and 3. We will examine two different cases. Let us start with case A, which represents a reflexive relation. Suppose we have a relation R1 containing the ordered pairs 1, 1, 2, 2, 3, 3, 1, 2, and 2, 1. To determine if this is reflexive, we follow the steps we established earlier. First, we check element 1. We can see that the pair 1, 1 is present in R1, so this condition is satisfied. Next, we check element 2. The pair 2, 2 is also present. Finally, we check element 3. The pair 3, 3 is present as well. Because every single element in set A is related to itself, we can conclude that R1 is a reflexive relation. Note that the extra pairs, 1, 2, and 2, 1, do not affect the reflexivity. They are simply additional relations. Now, let us look at case B to see what happens when a relation is not reflexive. Consider a second relation R2, which consists of the pairs 1, 1, 2, 2, 1, 3, and 3, 1. Let us perform the same verification process. For element 1, the pair 1, 1 is present, so that is satisfied. For element 2, the pair 2, 2 is present, which is also satisfied. However, when we check element 3, we find that the pair 3, 3 is not in R2. Because the element 3 is not related to itself, the condition for reflexivity is broken. Therefore, R2 is not a reflexive relation. Keep this distinction in mind, as it leads us directly into the next slide, where we will discuss some common mistakes students often make when identifying these relations. Common mistakes to avoid. Now that we have walked through the formal definition and some practical examples, let us discuss some common pitfalls to ensure you do not make these mistakes in your assignments or exams. First, let's address the concept of partial reflexivity. A very common error is assuming a relation is reflexive if only some of the elements are related to themselves. It is crucial to remember that for a relation to be reflexive, every single element of the set must be related to itself. To put this into perspective, if your set contains 10 elements, you must find 10 identity pairs, where each element is paired with itself, such as a comma A, within the relation. If even one is missing, as we saw in the non-reflexive example in the previous slide, the entire relation fails to be reflexive. Secondly, be careful not to ignore the set A. Students often make the mistake of looking only at the ordered pairs in the relation and forgetting to verify them against the original set. You must always refer back to the set A to ensure that no element has been overlooked. Remember, the relation is defined on the set, so the set is your primary checklist. Finally, do not confuse reflexive relations with symmetric relations. It is easy to mix these up, but remember that symmetry is about reciprocity, meaning if the pair A comma B exists, then B comma A must also exist. Reflexivity, however, is strictly and only about an element's relationship with itself. It is only concerned with the identity pairs, A comma A. By keeping these distinctions in mind, you will be able to analyze any relation with confidence. Now, let us move to the final slide to summarize the key takeaways of this topic. Key takeaways. Now, let us conclude our session by summarizing the most important points regarding reflexive relations. First, let's revisit the core requirement. Formally, a relation R on set A is reflexive if, for all elements in set A, the ordered pair A comma A is an element of relation R. This is the mathematical foundation we established in our formal definition slide. In simpler terms, this means that reflexive relations must contain all possible identity pairs for the given set. As we saw in our mathematical examples, these identity pairs are the ones where an element is matched specifically with itself. Finally, let's emphasize the failure condition. As we discussed when covering common mistakes, a single missing pair, a comma for any element, in set A makes the entire relation non-reflexive. It is an all-or-nothing property. If even one element is not related to itself, the relation fails the test of reflexivity.